Yes, so the goal is to report on an article of Yamano, and so before stating the result and proving it, we'll spend some time on setting notation and a few lemmas that will be needed during. Okay, so it's roughly quite similar to what Benoit explained this morning, except that now, instead of considering the complex plane, we consider Y Riemann surface that ramifies over the proper. And surjective. Okay, and so we'll use what happens on C to mimic the definition that was given by Benoit. And so we consider YR to be the inverse image of the disk on C. And we'll consider the ramification divisor, which is the logarithmic average on the order of ramification. Okay, so you recover the definition. If you take yes. If you take the identity, and so you use C to write this integral. Okay, so then you can mimic the definition. So we take X smooth projective variety. You take L line bundle and with a smooth Hermitian metric. And now, instead of considering map from C to X, you consider maps from the ramified cover over C, so Y to X, so holomorphic. And you can define so the order function as follows. So here you divide by the degree of the degree of the map, and you consider the same definition. Okay, and this is, so we define it up to 01. Because here you choose a curvature form on L given by H, and if you change it, it changed by 01, so as explained Benoit, and so we want it not to depend on it, so that's why we write it in this way. Okay, and so now if you fix the effective divisor, and you have to suppose that Y is not included in the report, so that you can put it back. And you can define the content function as follows. And you can truncate it here by putting the minimum between this number here and this order of vanishing along y. Okay, so basically this is the same definition as this morning, but here you just have to modify it a bit to include maps from arbitrary surfaces that can be sent to C and make it into a ramified covariance. Okay, so now we give a few recollection and lemmas. Okay, so the first one is, and just quickly rewrite it. So Nevanlinna inequality and comparisons. Okay, so we take the same setting as here. Okay, and so you have this theorem. So we write it as an inequality. So the term that Benoit is writing, so the little m is positive. And so if you look at the equality he wrote, it gives this inequality. Between the order function and the content function. Okay, so this is the line bundle associated to the effective divisor. Okay, and first lemma is follows. So if you take two line bundle X, and so now you suppose, and we can suppose that this will hold until the end of the talk, that F has a Variance image in X. Okay, so in particular, it will imply that this will always hold. So if L1 is less or equal than L2, meaning that if you tensor L2 by the dual of L1, this has a global section. Then you can compare the order function of L1 and L2. And if L2 is big, then can compare L1 and L2. Okay, so this will be referred to as comparisons. Okay, and so the proof are easy. Okay, so the first one, so you can write this as an effective divisor. Okay, by hypothesis. And so now, as this has the incidence image, this holds, and you can apply Nevanlinna inequality. And for this, okay, so since it's big by caudal lemma, you have that there exists a large enough integer that L2 less or equal. L1 is less or equal to L2 to the power n, and then you apply 1. Okay, so first, easy lemma. And so now I will recall this comparison. The logarithmic simplification formula. Okay, so I will denote like this because it's very long to write. And so proposition is as follows. So if you take a map of pair, such that so x, y are smooth projective, dy is a simple normal crossing divisor, dx is equal to f minus 1 dy. So by definition, this is the reduced part of the football.
Dy is not the same y.
No, yes. No, it's a map between a smooth projective relatives. And you suppose also that f is generically finite and surjective. Okay, so if you have this, you can compare the logarithmic canonical bundle on both sides. Then one. But if you pull back ky by f space or equal, then dx, and you have equality if f is finite and étale outside dx. dy. Okay, so this I will not prove. Okay. Quite classic. Finally, for this first part, we will state and prove lemma in the orthogonal. Geometry, so it will be lemma 2, so quite long to state. So you take BW smooth and projective. You take inside W is a simple normal cosine divisor. And you take P is generically finite, surjective. Total outside E, and such that P minus 1 E is also simple normal cosine. Okay, so with this setting, then there exists a birational modification such that, so first point, so you keep smooth positive variety. If you pull back E by P, you keep a simple normal cosine divisor, and the most important part is the following. You pull back logarithmic American bundle phi by C. It's less or equal than yes. Yeah. I think this is okay. This you. Oh. Yes. Yes, yes, yes. Okay, so this. So we give the proof. And so basically, lemma 1, lemma 2, and the logarithmic ramification formula will always be used in the proof of gamma noise result. Okay, so first you take a flatification of P. So, which is a result of Raynaud and Gruson. Where, so these are smooth, so this everything will be smooth always, so I will stop writing it. So U1 is isomorphism outside E, and T1 becomes finite. Okay. Okay, now by Hironaka, in solution of singularities, you can consider the map with two irrational, which is an isomorphism outside T1 and T minus 1, T1 minus 1 is a simple normal crossing, and still it's W2 is smooth. Okay, so now you denote to have this same equation as in the statement. This W2 and big tilde de fiber product over W1. So you have the projection here, here, also. I said, everyone, I will not write it anymore. Everything will be smooth. Okay. Here you said you can only have normal. Then you will resolve. Okay, so maybe. Okay, so if for this result you can only have normal, then I guess yeah, you resolve it afterwards at this step. Okay. Then I misquoted that. Okay. So with this, okay, so you have then so the diagram of the statement. We need essentially this finite and et al. Outside this. Okay, so this gives 1 and 2. And so for the third part, okay, so as P till this finite et al. Epsilon. Which is simple normal crossing. You have the equality case and the logarithmic ramification formula, which give you that of this is equal yes, this by commutativity of the diagram. Now, since this is simple normal crossing, the logarithmic ramification formula gives the inequality. Okay, and so now if you use this, with this you find the well, the formula that was here. So this gives okay. And so now we come to the result of Emanuel. So the test statement goes as follows. So first, so there is a conjecture. So quite a strong one. So we'll call it C, that says if you're in the same setting as in the beginning, and you assume that so the effective divisor is simple normal crossing, and the line bundle is ample. So you also assume, as I said, that F has Zariski-Dense image. Then one has the following estimates of the logarithmic canonical bundle is the truncated at order 1 order function. And so this means that is all outside exceptional set, as in the same sense of that Benoit recalled. Okay, so a remark is that if this holds for L ample, it holds also for L big. And for this, as L, you use the so first lemma and the part with the, you will be able to compare L ample with L big and have the same thing here. Okay, so nothing deep here. Okay, and so the result of Yamano is now the following. That if you assume that the conjecture, so the conjecture, so it's the same setting and it holds for every SNC divisor, every Riemann surface, that is a ramification of C, and every F from this Riemann surface to X that has Zariski-Dense image, then this, so this is the conjecture. And so if you assume that C holds for any smooth projective variety that is birational to a given model, say Xn, so of dimension n, that is birational to a given model, so well, and typically we take an abelian variety. So this is what he does in the article. Then the conjecture holds in general. So if you assume that the conjecture holds for any smooth projective variety of dimension L, that is birational to a fixed model. So say you fixed a variety and look, and if you can prove the conjecture for all the varieties that are birational to this model, then the conjecture will hold in general. As far as I've understood from as far as I've understood. He states birational to an abelian variety, but as far as I've understood the proof, it plays no role. The fact that and I think the abelian case must be the only one where there are some strong information about this statement. So that's why he tries to reduce it to this. And now, okay, so we give the proof. So I think I will have only time for the first step. I explain quickly the last one. So first, we consider X a smooth projective variety endowed with a generically finite map P from X to your fixed model. Generically finite. And subjective, of course. Okay, so first you take G in A, a reduced divisor. Such that P is finite étal outside G. And up to adding a reduced component. Suppose that so SNC divisor D is included in and so now apply Nevanlinna's theorem to find birational modification with so ethyl smooth T minus 1 G and T minus 1 G simple normal crossing, and P is an isomorphism outside G. So now you apply lemma 2 to tilde. This, so and you find another birational modification. Okay, with this in here. With this and this smooth, this simple normal crossing, and the inequality. Okay, so this, so what the lemma 2 tells you, so the point 3 of the lemma gives you this, this inequality. Okay. So now you consider the lift of your map to spaces. So you have of F. Okay, and so with this inequality and comparison lemma. You get this inequality of the order function. So this is for this function. Okay, so you get the inequality with P star here, but you can put it here by punctuality of what this means. Okay, so now you apply what you know, the hypothesis of the main theorem of Yamana's main theorem here. That so you can apply the conjecture for. So here you this. Here it's F double. So this is birational to A. So you apply to, you use this bundle. Okay, so this will be big. As I said, it's okay to consider big line bundles. And this simple normal crossing divisor. And so if you do this, so you obtain the following estimate. Yes, so now you can check that. So this you can replace with with this the fixed ample line bundle that you fix on the, let's say, you fixed on X. Okay, so I mean this is essentially because you have this. And this one is big, so you can compare it. And the second observation is truncated order function here. Okay, and so here it's essentially a game of writing with the commutativity of the diagram using the equality, but because the divisors are SNC. Okay. Okay. And now if you combine so this observation and the two inequality here, you get that so, okay. Okay, now you write this minus 1 d plus f effective. Yes, so first, okay, so which is completely straightforward, that you have this inequality. Um, yeah, which is, I mean, you just replace it, what it meant here. Okay. And the second one is that you have this is Okay, so this is equal this, and this is less or equal than the same number, which is not truncated. And so now you use the Nevanlinna inequality. So you see that here and here. Okay, and so you replace the 4 and you find this inequality. Okay, well, as I said, because the subtraction of this and this is an O1. Okay, and so now since it is SMC, the logarithmic simplification formula gives that this is less than this, and with the comparison lemma. Okay, and so with this you have the equality that you were looking for, the inequality that you were looking for. Yeah, so that was for the first step. So now the second step is so the general case. And so you consider, so you have X general, and you consider simply X times A, and by considering an adequate subvariety of dimension X. So you have so this subvariety inside X times A with two generically finite morphisms and subjective. Okay, and then you play a game similar to what has been done in the step one, and it's you do birational modification to you reduce to the case of step one, you apply it, you do the same trick as this step three, and you can find that the estimate holds in general. But here it doesn't use anywhere that you really have an abelian variety. You just use a correspondence and you apply the result that you've had. And that's okay. I will stop here. Yes. No, it was Archimedes, and it's basically simply to ensure that, as far as I understood, that you can pull back the divisor always by okay, so it actually appears in the calculation of the step two. This because here, not really. So actually, in the formula for the step two, it is crucial to have to catch another one. At some point, you have a formula that makes the ramification divisor simplify as you want. But if not, I think this formula does not hold, that's for sure. And so what? No. They have same dimension. That's just it. And that's what I said. Is that it can be any model that you fix, but you have to prove the conjecture for any smooth projective variety that is birational to this model.
So the statement is for a given n. If you have one model of dimension same dimension.
Yes.
So this is the statement.
But you have to prove it for any variety birational to your model, and for any map, any simple normal crossing divisor.
So here we never switch to map.
No, it appears in the yeah. Would suppose so. I haven't thought of this improvement. Yes, you change the transformation. You can manage step one. No, but it have so the fact that it's that you truncate at under one, and that you have to allow one map appears in step two. But it's as technical than the first step.